use of Fleming's right-hand rule. The ideas are just the same as Fleming's left-hand rule, but this time it's instead of force, it's the motion that we're going to look at. So yeah, those are the two objectives for this session. We have 30 minutes, so we will, as much as possible, interact. You don't understand something, raise a question somewhere in the middle.
Okay.
All right, so let's take a look at I got Lenz law up here on a screen for you. Now, Lenz law, it actually is that induced current always tend to oppose the cause which produces it. What does that mean? Lenz's law, we're talking about, remember, induced current and induced voltage. So induced current is something that a current that is produced as a result of some relative motion. Okay, so relative motion produces induced current, and induced current needs the induced voltage, which is called electromotive force. You remember EMF?
Yes.
No.
Electromotive force, EMF.
Yes, yes.
Oh wait, yeah.
Yes, EMF for electromotive force. This is the voltage that needs to drive the induced current. Induced current, like we said, do you remember the setting? We had a magnet, north and let's say south. A current carrying conductor is placed and a galvanometer is connected. That's what we saw. Moving this part of the conductor in the magnetic field, it disturbs the particle producing the current. That current produced is called, everyone talk to me?
Induced
current.
Yes, induced current. Okay, good. That induced current is the one that comes about by moving the conductor in the magnetic field, and the current that is produced is called induced current. And that induced current produced is the one that is driven around the whole circuit by the EMF. Is that clear?
Yes.
All right.
Yes.
So electromotive force is the one.
Yes.
Right. That's the one that does that. Now, the Lenz law, it actually is that induced current here. The induced current always tend to oppose the cause which produces it. What does that mean? It means that when, let's say, this time it's a permanent magnet, not a temporary magnet, but it's a permanent magnet. When the permanent magnet is moved in and out of this solenoid here, what happens is that again, this is basically a conductor, the solenoid. The coil here is a conductor. So what happens is the same idea of moving a conductor in a magnetic field. We get a magnetic field produced by the permanent magnet, which is when it's moved in and out of the solenoid, it disturbs the particle arrangement again, allowing current to flow. So when current flows, it is detected by the galvanometer down here. And so current continues to flow, even though it is not connected to some electricity source. Now, the question is that to really understand the law, what it means by induced current always tend to oppose the cause which produces it. The cause is that moving the magnet in and out of the solenoid, that's the cause. But when current is produced in the coil here, current produced in a direction. The direction actually determines this part here. It tends to oppose. Now, by looking at the diagram here.
Oh.
Yes? Continue. So the knot end is brought closer. When the knot end is brought closer, the current flows in such a way that when the knot pole is brought closer, this end of the solenoid, and P is the one that tends to be a knot end. Do you know why it has to be a knot pole? I am going to explain. Why this has to be the knot pole is simply because when the knot pole is brought closer, current flows in this direction, the direction that is indicated, so that using your right hand grip rule, do you remember?
Yes.
Yes? Using right hand grip rule, we can identify this as the thumb always. Remember, right hand grip rule. Thumb always points towards the knot. Do you remember? Fingers give you the current direction. Thumb gives you the knot pole. Thumb always points towards the knot pole. Who's that?
Who's that? Who's there?
Guys, mute yourselves,
Guys.
please. This is not funny.
Hey guys, you got to behave because otherwise I'm gonna. It's no good. You keep silent. You're on mute, and I'm the only one talking. I want us to interact. Okay?
Yes.
Please
Yes,
try to
ma'am.
minimize.
Okay.
Try to minimize unnecessary noise.
Yes, Mr.
So using right hand grip, we identify the knot pole here. Now, on this end, you got knot pole, current flows producing this to be knot pole, knot pole. What happens when you bring a knot pole and a knot pole together?
They repel.
They repel. So it is basically current flow to oppose.
Guys, mute them. Mute your player, please.
Yeah.
Did you get that?
Yes.
Yes, Mr.
Okay.
Peter, Ryan. Okay.
Now let's move on to the second one here, B. B.
Hey.
This time the knot pole is pulled away. When the knot pole is pulled away, what is happening is that current actually changes the direction. Can you see the current direction changing from here? It's going up that way, but down here it's coming down. Can you see that?
Yeah.
It is.
Yeah.
Yeah.
It always tend to oppose the cause. Cause is that moving the magnet away, current moving in the reverse direction. Turning this end, when using your right hand grip, this and P here, it becomes the south pole. Q is the one that becomes the north pole. Why that has to happen? Because now we have a south pole and north pole, two opposite poles. They're gonna attract each other. So it again opposes the motion. So every single time when the magnet is moved in and out, current direction constantly changes. Is that clear?
Yes, Mr.
Thank you. All right.
Yes, Mr.
Now let's move a little bit further down. Lenz law, continuation. This time, instead of moving the north pole, the south pole. South pole in, south pole out.
Tell me.
Okay, so what happens is just the idea is just the same as the one above. If you can understand the previous setting, the one that I've just explained, then the second setting here, this is going to be just the same. C and B is just the same as A and B. If you got any further question on that, we're going to talk more about that in class.
Mr. What?
Come again?
Yo.
Mr. Frel.
Yes.
Mr. What page is this on on the success physics textbook.
6.
I don't have the text.
6.
I don't have the textbook with me right now, but did you pick up the worksheet that I gave out?
Yeah, Mr. It's on the worksheet.
It's on the worksheet.
Oh, okay.
Yes, yes.
Google Drive.
Which worksheet?
Okay.
The one that I just produced with one
Okay,
of those
thanks.
videos.
Oh, the one you gave last week.
Yes, yes,
Okay.
that's the one.
Please.
Yes. 6.
Wait, Mister. Oh, yeah.
Oh my God.
All right.
Guys, concentrate.
Okay, now here, class, notice this. Do you remember the law of conservation of energy?
Yeah.
Yes.
All right, conservation of energy states that energy is neither created nor destroyed.
Not destroyed.
That's right. It changes from one form to
Another.
Okay, Wallace.
another. That's right. So Lenz's law is basically it actually upholds the law of conservation of energy. And so if you got this bit of the, we can actually take a look at this bit. It can be explained by the principle of conservation of energy. What does that mean? Well, it means that when the magnet is moved towards the solenoid, current is induced in the solenoid, which means that why does this occur? Well, electrical energy can never be created without any form of work being done. So once work is done now, we say that work is basically when energy is converted from one form into another, we say work is done. So that's basically that. Now moving this magnet in and out of the solenoid for both cases here, the needle deflects, telling us that current moves in different direction, and that comes about as a result of to really uphold Lenz's law. Here are some of those points from A, B, C, and D. You can spend some time, check those ones out, but let's move a little bit further down and check out Fleming's right-hand rule. Fleming's left-hand rule is the one that we use to identify the current direction given the magnetic field and the force direction. This time it's Fleming's right-hand rule. Now the direction of current induced in a conductor moving at right angles to and cutting across a magnetic flux can be determined with Fleming's right-hand rule. Now take a look at your right hand, hold up your right hand, and there is this diagram that is given down here. This diagram here. Can you see this?
Yes.
All right. The thumb, in our previous discussion, Fleming's left-hand rule, the thumb gives you the force direction. Do you remember that?
Force direction.
Force direction. Well, whereas the finger giving you the field lines and the second finger giving you the current direction, the thumb giving us the force direction. But in this case, the right-hand rule, thumb giving you the motion of the conductor in the magnetic field. So take a look at this diagram here. We're going to use Fleming's right-hand rule. Motion is what? It's going down this way. So your thumb, you have to change the position of the thumb. And field lines actually they run from north to south. And motion is going down that way. If I'm going to ask you, or if I'm going to say, in which direction should current flow in this conductor? Let's say this side is side P and that side is side Q. using the right hand grip, not right hand grip, Fleming's right hand rule. Let's try to figure out the current direction. Is it going from P to Q or Q to P? Tom is going down this way, P line is going that way. So current is coming from Q to P, right?
Yes.
Yeah.
Do you understand current coming from Q to P?
Can you explain it again? I don't.
Sir,
Okay, use your right hand. Use your right hand. The thumb is the one that is going down this way, going down into the from north to south. Field lines running from north to south. So your fingers are going down, going this way. And current direction. Can you see current direction? My second finger is coming out this way. It's coming from Q to P. Can you see that?
Yeah.
Yeah.
Gonna be upside down. Some shit.
Yeah, QP,
Right.
yeah.
If it is not clear for some of you, then let's take a look at some examples and try to understand that even more.
Yes,
Okay.
it is.
All right, let's take
Yes.
a look. All right, okay, stay with me. Let's take a look at this example here.
Always.
Oh, won't you?
Take a look at this example here.
Whatever.
Okay, and then
Yes.
Yes.
here I got this
Okay.
example, and the example reads the
Yes.
Yeah, that's me.
the figure actually shows a conductor PQ, which moves to the left on a plane of metal wire connected to a galvanometer. So it is moving to the left. This is the direction to which it is moving. Yes?
What is that?
Are you with me?
Yes, Mr.
Okay. Can you see this? Can you see the arrow? It's moving to the left. Field lines always run from north to south, right?
Yes.
That's right. Field lines going from north to south. So use your right hand again. Right hand.
Yes.
The pointer always points towards north to south. So this is my pointer going from north to south. Force is going out this way. Movement coming out this way. So current, will it go from P to Q or Q to P? You try to figure it out and tell me.
P to Q.
P to
Q.
P to Q.
very good. P to Q is correct.
It says right there, so.
Do you understand the use of Fleming's right-hand rule?
Yes.
Yes.
Okay, that's better. Now let's take a look at another example. Let's take a look at another example. You ready for that?
Yes.
Okay.
Yes,
take a look
Mr.
at- Let's take a look
Ready,
at
steady.
this.
Naomi, take it easy.
Mr. All these on the worksheet you gave.
Yes, yes.
Yeah. Page 460.
Thank you.
Thank you, Naomi.
Thank you, Naomi.
All right. Now let's take a look at the second example. Second example is not as easy as the first one. This time we have you got a solenoid.
Are you serious?
It's connected to some force. First of all, let's identify the current direction. Tell me which direction does current flow?
South to south.
Is it from positive to negative or negative to positive?
Positive to negative.
Very good, positive to negative. So in this case, current is flowing this way. I am actually giving it a current direction. Can you see that?
Yes.
Yes.
This is this is the current direction. This is a solenoid.
Yes.
I would like you to tell me P, the part that is labeled P here. Will it be the North Pole or the South Pole? Use your right hand grip rule and tell me.
South. Yaman. Wait.
North.
North. North.
South.
North.
You sure about
Where
that?
are you ready?
He said
What
south,
else?
so.
South pole, south pole,
Yung head no.
It's north.
Yes.
south pole.
Yaman, I think it's
Oh.
north.
How is it?
It's
How?
south.
Can take a look at your
No.
screen. I got
But
it up
it's
there
from
for you.
Yeah.
Look at your screen. It's the south pole, yeah?
Yeah.
Ah, exactly. I said that. Hey.
Mr.
That's south pole.
Can you explain?
Mr. What,
Can you explain how?
What is it?
what's going on? Mr. We don't get it.
Point your
Look at
fingers
that
in the
direction.
The card. Okay.
Let's do
Mr.
that again. Here,
Pakulo south eh?
current coming this way.
Okay.
It's going right behind and it's coming back this way. Can you see it? Are you following?
Yes.
Yes.
Okay, so current is coming back this way. And so use your right hand grip rule right now. And you said that fingers, they're going to give you current direction. Yeah? Thumb is pointing
Yacht.
Thumb is pointing downwards, so this becomes your thumb will always point towards the north pole, so that means that this is the south. You got that?
Oh.
Yes, Mr.
Yes.
All right, that means that this is the north pole. If this is south, that's the north pole. Field lines going from north to south. It's coming this way. Can you see that?
Yeah.
Yes.
Okay. Now we got a field line given, and the second part of the whole story says that when the following figure, a current is induced in the following figure, current is induced when the U-shaped iron core is moved upward. What does that mean? When this U-shaped iron core is moved upward, it means that this current carrying conductor, in other words, the current carrying conductor is moved downward. Is that clear?
Yes.
Yes, sir.
Right. So current, the motion conductor is moving down this way. Not, this is the north pole, that's the south pole. Use your right hand grip rule and, not right hand grip rule, Fleming's right hand rule.
Fleming's right hand rule.
Fleming's right hand rule to tell me the current direction. Let's do that together. Feeling pointing from north to south. Course thumb is going down this way, it's going down, and current, tell me, it's going from X to Y or Y to X?
X to Y, I think.
White
to Y.
words. Yaman.
X to Y.
X to Y.
X to Y.
X to
X
Y.
to Y is
X to
correct.
Y.
That's right. So current is actually current flows from X to Y. That's what happens.
Okay, Wallace.
You got that?
Yes.
Yes, Mr.
Yes, Mr.
No, Mister, can you explain that again? I don't get that.
Which part?
No, I didn't get that.
Which part? Where do I start?
This is the last part.
Just the last part?
Yeah, like, can you like just explain that again?
All right. Here's the one. Current direction, current is flowing from positive to negative. Yes?
Yep.
Current is going this way. It goes right behind this iron core and it's coming back this way.
Mm-hmm.
We used to
Using this current
write
direction
them solenoid.
and your right hand grip rule, thumb points downward. That means that this is the south. That is the north. Field lines, they running from north to south. So this is the field line. The iron core is moved downward. That means that, iron core is moved upward. That means that the conductor XY is moved downwards. So this is what I got. Field lines coming this way. The movement is going down that way. So using again Fleming's right hand, the pointer points towards, it's going from north to south field lines. Thumb points towards the motion of the motion direction. The conductor XY, so it's going down this way. So which means that the second figure is the one that is going more like into the page. So you're saying that current direction is actually going from X to Y. Is that clear?
Yes.
Yes, Mr.
All right, okay. So that's basically that. Try to check out similar questions from your PYB and try to answer them. If you cannot, you come back and talk about it in class.
That's if we come back to class.
That's it. Okay.
I'm done for it.
Time is catching up. Finally, these are the factors that determine the induced current. First of all, okay, first of all, these are the factors that they affect the induced current. Number one, the magnitude of induced current increases when, please make note of this, very important, the speed of relative motion. When speed increases, it also increases the induced current. Number two, strength of the magnetic field. When the strength increases, it also increases the induced current. The next thing is length of the conductor. When the length increases, it also increases the induced current. And the second point is the magnitude of the induced current is maximum. Remember this formula? F is equals to
BIL
right,
sin theta.
Sin theta.
Arasha, Bill.
So when the sine theta, when angle is 90 degree, what happens is that sine 90 giving you 1, which will produce a maximum force. So with that understanding, you notice that the magnitude of the induced current is maximum when conductor cuts the magnetic field perpendicular. What does that mean? It means that when it cuts the whole magnetic field at 90 degrees.
90-degree angle.
So these are the important factors that affect the induced current.
Mr. Page.
458.
These are very important points.
Naomi, take it easy, please.
All right, class, that's basically that. I hope you learned something from